Let's explain implicit differentiation through an example. Here is the question. If x squared plus y squared equals 25, this will define y as a function of x. We want to find the derivative of this function at this point. This point is on the graph. You can easily check that when x equals to 4, y equals to minus 3, and left-hand side is equal to 25. Okay? Now, the usual way to do this would be try to solve for y explicitly in terms of x, and then take the derivative using the usual differentiation rules. That could work for this problem, although it is a little bit tedious to work out the details. Let me just briefly mention the steps, and I'll leave the details for you to digest. So first you solve for y. You move x to the other side. So you got y squared equals 25 minus x squared. Then you take a square root on both sides. When you do that, you have to be careful. When you take a square root, there could be two solutions, positive or negative. Here, you have to take negative square root because y is equal to minus 3. We are looking at this particular point, so y is a negative, all right? Now, we want to find its derivative, so you rewrite this in the form of 1/2 power of this expression. And then you use the generalized power rule to find the derivative. And then once you have that, you just substitute x equals 4, y equals minus 3 to get the answer, okay? As you can see, it does work, but that is not what we're trying to discuss here. We're going to focus on this new technique, implicit differentiation, all right? The idea of implicit differentiation is to bypass this process of solving for y. So we're not going to solve for y in terms of x. What you can do is to take a look of the equation and then take dx on both sides of the equation. Okay? So when you do that, let's do the first term, x squared. That is easy. That's simply a 2x. Now, what is the derivative of y squared? Well, you will probably say it's equal to 2y. That would be correct if you take dy. But here we're taking dx derivative with respect to x. You have to treat y as a function of x. In other words, you think about y squared as yx. Yx is a function of x, okay? And then square of that. Now, how do you take its derivative? Well, this is a composition function. So it's the function x squared and then y equals yx. So you have to use the generalized power rule, which is a special case of the chain rule. Let me remind you that rule here. So generalized power rule says if you have u to the n, where u is a function of x, to take its derivative, you just apply the usual power rule. In other words, move n to the front and then subtract this by 1. But then after that, you have to multiply by the derivative of u. Okay? So apply that to this function here. Therefore, derivative of y squared becomes, okay, first you apply the usual power rule, which gives you 2y, and then you have to multiply by derivative of y, okay? Okay, so that is the derivative of y squared. Therefore, you're going to have 2y dy dx, and then derivative of 25 is just 0, okay? Now, you want to solve for dy dx. Well, you can just move 2x to the other side, and then divide both sides by the coefficient. Before you divide, we can actually cancel out the 2 on both sides. So then you simply divide it by y here. All right, so therefore dy dx is minus x over y. And then you simply substitute x equals 4, y equals minus 3, and that will give you the answer. Okay? So again, the idea of implicit differentiation is that you do not need to solve for y. Instead, you just take a derivative with respect to x on both sides of an equation. And when you do that, keep in mind that y is a function of x. Okay? Let's look at another example. Here we have the following implicitly defined function. Y. We have this equation between x and y, and from there y becomes a function of x, and we want to find the dy dx. Okay, so for this problem, it is much harder to solve for y, and therefore the solution 2 that we saw before is not very practical. So let's use the implicit differentiation here. Again, you're going to take a dx on both sides of the equation. Okay, so you're going to do it one by one here. So 4x to the fourth power gives you 4x to the third. That is simply the power rule. And for the next term, 3x squared times y, you have to really think about this as a product of 3x squared and then y. So the product rule says you're going to take a derivative of the first function, which is 6x and then times y, plus the first function, which is 3x squared, times the derivative of y, which is dy dx. Okay? And then you're going to deal with the 4xy squared. Again, I'm going to treat this as a product of 4x and y squared. I'm also going to put a parenthesis around the answer because there's a negative sign in the front, so minus this whole thing here. All right, so what's inside the parenthesis? We apply the product rule, so f prime times g. F prime in this case is just 4, and g is y squared. Then plus f g prime. F is 4x, and derivative of y squared, again, we have to use the generalized power rule. Just like before, this should be equal to 2y times dy dx. Okay? And then derivative of 25 is simply 0. So now we have this equation here involving dy dx. You can solve for dy dx from this. Basically, you group the terms that contains dy dx together, and then the remaining terms together. So we're going to get those 1, 2, 3 terms here. They do not contain dy dx, so group them together. And then these other 2 terms do contain dy dx, so you group those together. And now you take a common factor dy dx out. So we got the following. And then to solve for dy dx, you move this whole thing to the other side. So once you move this to the other side, you get the following. And then you simply divide both sides by the coefficient of dy dx. And that is your final answer for this problem. Let's look at another example involving with second derivative, y double prime. So here we have the following equation. We want to find the y double prime. Here r is a constant. Again, we can do this using implicit differentiation. So we're going to take a ddx on both sides, and that will allow you to find the y prime first. Okay. So when you take a ddx, x to the fourth power simply gives you 4x to the third. For y to the fourth, again, treat y as a function of x and apply generalized power rule, and that gives you 4y to the third, and then times the derivative of y with respect to x, which we denote by y prime. Okay. And then from here, you can solve for y prime. As before, you move 4x to the third to the other side. You can also cancel out the 4 on both sides, and then divide by y to the third. So anyway, it gives you minus x to the third over y to the third. That is your y prime. Now we need to compute the y double prime. We simply take this expression and then take its derivative to get y double prime. Notice this is a quotient, so we do need a quotient rule here. The rule says you take the derivative of the top, so f prime g minus fg prime. So that's f prime in this case is 3x squared. Okay, that's what f prime is, times g is y to the third, minus f times g prime. F is x to the third, and then g prime is, now here we have to use generalize the power rule. Keep in mind that y is a function of x. So we have a 3y squared, and then times the derivative of y, which is y prime. The denominator is simply equal to the square of the previous denominator, so y to the 6th. And we keep the minus sign in the front. Now, we need to express the final answer in terms of x and y only. That means this y prime will need to be replaced by this expression. So let's do that. And we got the following. As you can see, we moved the 3 to the front, and then y squared as well, and then y prime is replaced by this. Now the rest is just some algebra, standard algebra. You can combine the minus sign to become the plus, and the y squared cancel out with y to the third. So we got the following, and we also combine the x to the third with this x to the third to get x to the 6th. We are almost there. We still have a fraction inside the fraction. To get rid of the denominator here, we multiply top and bottom by y. So we do the multiply by y here, and then once you multiply y into this, then this y will cancel out. So this is your final answer here.